Okay, in this video segment we're going to get into the specific definition of the various properties on the stress strain curve. Please take note that these words that you have here, stiffness, resilience, toughness, strength, all of those first four are ones that in the psychological world have a very specific meaning as well, personalities and things like that. These words have been purposely chosen to be related to how we think about personalities. So for instance, stiffness is something here that the ability to accept large elastic loads with little deformation. Now that parameter we'll use is called the modulus of elasticity, and in a lot of materials you'll see early on that when we load it up with a little bit of stress, there's a little bit of strain, and if we were to unload it, it would go right back down to absolutely zero deformation. We call that elastic behavior. And that proportionality between stress and strain is what's called the modulus of elasticity. It is the slope, oftentimes shown in this kind of fashion, E over 1, rise over run, right? It is more broadly, you could think of as taking anything in there and taking the change in stress over a specific region divided by the change or the delta strain, right? So it's going to have units of stress over strain. And Hooke's law is for this elastic region, and so you'll see that as written as sigma equals E epsilon. That stress is linear in relationship to the strain, and that slope or proportionality constant is our E. This is also known as Young's modulus, because Young and Hooke at the same time came up with this kind of model for material behavior. And it turns out that there's a little bit of, back in that era, instead of having rock stars competing to see who was somehow better than the other, we had scientists competing to see who was better than the other. And so that's why we end up with two different names. One's about the general relationship here, and the other is about a specific value within that relationship, really talking about the same thing. So a material that is stiffer will have a higher value of E. Now, E for steel, for instance, for most of them is right around 29,000 KSI. That's 29 million PSI. E for concrete, on the other hand, is much lower. It's about an order of magnitude lower. There's a lot of other variables involved. There's not one value, but it's in the region of about 3,000 KSI. So concrete is much more flexible than is are most steels. Now notice again the usage of this psychological word, a stiff personality. That's one maybe that you have to put a lot more force to get them to change or do something in a personal or people kind of way, versus somebody more flexible it's a lot easier to get them to change or do things, right? And so again, these words are chosen specifically associated with that. Right now, E is also called the tangent modulus. That means the slope anywhere, but usually when people talk about E, they're talking about E naught, and that's in that linear elastic region. So elasticity doesn't mean necessarily linear. It could. Elastic just means I follow the stress-strain curve, and when I unload, it comes back exactly on that curve, and I have no permanent deformations. Right? Now, this particular steel is not like that. It's linear elastic as it goes up the curve until it hits the proportional limit, which means that this is no longer a valid relationship. It's no longer linear. And then it starts to curve over a little bit. It gets to what we call an upper yield point. And if we go beyond that, if we were to unload, we would unload at the same rate or slope as the elastic region. So that'd be unloading into the plastic, and we would end up with plastic deformation out here, right? Permanent deformation. Right? So this yield point that we have, and oftentimes when you have this little tiny bump like that, we kind of ignore it, cut it off, call it one specific value, but some steels will have multiple ones. But that will be our yield stress that corresponds then with the yield strain. Right? And yeah, sigma yield would equal E naught strain yield. Right? And you'll have seen that in the previous notes that was a little bit at how E was defined, sigma yield over E, or strain yield. And that's just fine so long as we truly have straight line all the way up to that point. Right? That's the yield stress. And the energy that is associated with taking our material up to that point is what we call the resilience. And that's represented by this triangular area right there. So there's your resilience. The value becomes then the modulus of resilience, and that's given the symbol U sub r. Not everybody uses that particular symbol, but that's one common one. Area under the elastic portion of the stress strain curve. Here that would be really easy. It's just 1/2 of the base times the height because it's a triangle. But notice what you're going to do is in effect integrate is the area of something about the stress versus the strain, and we'll do that in the y-axis. So as we gradually go up from one limit to the other, that in this case would be 0 to the yield strain. Notice the units. We're going to have a force over area, right? So force over area is strain. Do this down here. Force over area is strain. And then we would have the strain, which would be deformation over the original length. Right? And note what's going to happen. That's really force times the deformation. That's work of the associated with the deformation over volume. So if we integrate then this whole thing over the volume of the member, we get the total amount of energy. And that's all to go back and say, that's why resilience is the ability to absorb elastic energy. Right? There's two key things there, elastic and energy that's really happening. Right? That's resilience, and the more area we have there, the more resilient that particular member. But some materials can deform in a huge way past than that initial yield, and that would be the case for a lot of steels all the way out to this rupture strain. It's way out here to the far right, and so that would be your sigma r, or sometimes people will call that fracture. It's the same meaning, two different words. So subscript F there. So sigma strain fracture, strain yield over here. This area that's left over here is going to be associated with plastic energy. So resilience is elastic, out here is plastic, and take the two all together, talks about the total amount of energy to get to rupture. That is what toughness is all about, that total amount. Right? Strength is the ability to accept large loads without rupture. So in this case we have a yield strength, and we have what would be called the ultimate strength. That's this peak on the stress strain curve. When you look at the videos of some of these members when they are tested to failure, then you find out that what's going to happen right when we get to this peak, we'll have some dramatic necking, narrowing, just like a person's neck is narrower than their shoulders. We'll have a dramatic narrowing, which means the cross-sectional area is now significantly different than the original. And so true stress and strain will then take our axial force, divide by the true amount of area, and this will kick off and go high. But if we use the original one, original cross-sectional area, then this thing falls off, and its stress, the amount of stress, the load that can be handled actually goes down, and that's why we see this drop off. So sigma ult is this peak on the engineering stress strain curve, and then we get out here to this this rupture stress that's out here from an engineering standpoint. And that's we have more than one kinds of strength. Ultimate stress or ultimate strength and yield stress and strength are the common ones. Ductility is the ability to deform before rupture, normally characterized by a large plastic region. Right? So ductility can be, well, the ratio between the fracture strain and the yield strain. Right? Or it could also be, that's on a deformation basis, or it could be defined by this total energy that's the plastic energy. It's another way to do it. Brittleness is the opposite. It's like chalk, right? You take a piece of chalk and bam, when you break it, there's very little warning of impending failure. It just happens almost instantly. Brittleness would have very little of this energy sitting out here. Now in the next examples, we're going to go and apply this, understand these properties in a much more detailed way.